Hello everyone, today we are bringing you an explanation of the CKS exam questions, and next up is the fourth question. This question is mainly about a high-risk operation involving a pod. The background of this question is that a pod is accessing the physical memory of our host machine. This is actually a very dangerous behavior because when we access the memory device file under structure dev mem, it's typically used for memory dumping, and it can also involve side channel attacks and other related issues. So, if a pod is accessing this, what does that mean? It means that, well, we might be under some kind of attack. So, what do we need to do here? We need to use detection tools to check exactly where the problem lies and which pod is causing it, and then set the replica count of this problematic or abnormal pod to 0. This effectively stops the pod from functioning. However, this won't affect the deployment itself. It just means we've shut down the pod. Because in our system, the memory under dev is actually a character device file for our physical memory. Reading from or writing to it can actually allow access to raw data within our system, such as memory structures, as well as keys, passwords, and other related content from other processes. So, under normal circumstances, even if a container is running as the root user, it is not allowed by default to access the dev mem on our host machine. Therefore, we need to detect this, find the pod, and shut it down. So for this problem, our main approach is to first detect this abnormal pod and then change the number of replicas for this pod to 0, which will allow us to shut down the pod immediately. Now let's take a specific look at the solution to this problem. First of all, the main point of this problem is the first step. We definitely need to figure out what to do first, which is to find where this pod is. So what is the first thing we need to create? Create our scanning rules. By using our scanning rules to scan, we can extract the specific information of the pod, such as which pod is accessing or even which container is accessing. So, we use this container ID. Generally, we can find the container ID through this command and then use the container ID to find which pod this container ID belongs to. Finally, in our configuration file, we turn off this pod, which is equivalent to deleting it. This is our solution to this problem. First of all, this problem is mainly divided into two parts. The first part is to edit our scanning rules. The second part is to perform the corresponding operations after scanning out the content. Alright, let's take a specific look at how to solve this problem. First of all, the first step is still to remote into the corresponding host. Also, for this problem, we need administrator privileges. We need to use administrator privileges for this one. So our first step here is to remote into the corresponding host, switch to administrator privileges, and then proceed with rule creation and scanning. Now let's continue to see how to solve this problem. First of all, let's remote into the corresponding host. Okay, first step, let's remote into our corresponding host, and then what do? We perform the privilege, which is actually just switching to administrator privileges. We switch to administrator privileges. Here it's equivalent to us now having root user privileges. Next, let's take a look. First, in the current namespace, the deployment information includes these. So here, this is the current deployment, which is what we are going to deal with in a moment. Next, the first step is, since we don't actually know where it is right now, we need to do what? First, create our scanning rules, and then use the scanning rules to do what? To scan the contents of the namespace we are currently in. After scanning, what will it actually scan out? Actually, what it will ultimately scan out is the specific container ID. Because we are accessing this memory, you can't really say the pod is accessing it, since the pod is just a framework. What we can ultimately access directly must be the container, because it is the container that finally accesses the system memory. So, first of all, we are going to create our content here. Since there is no content in this file, we will write it from scratch here. Just writing it from scratch is fine. Here, everyone needs to pay attention to the indentation. Pay a little attention to the indentation. Okay, so next, for the first line here, you can keep it, or it doesn't really matter if it's not there. It's just a comment. And then next, let's create our scan. And since we mentioned it in the topic earlier, what is the problem we are currently facing? That is, what exactly was scanned? That is our memory. To be precise, the path is memory under the dev directory. This file was scanned. So, first of all, we need to write out this path. Let's write out the path first. And next is a specific rule. The naming of the rule. Here, we can just use dev memory. This name will do. And for the specific description, you can actually write the same thing for both. It doesn't have much of an impact. And next is the main content, which is our specific scanning steps. Let's take a look at how to write it specifically. After writing the basic description, the next part is the actual content. For the actual content here, first of all, the indentation should be aligned with the one above. And for the first part, what do we need to write here? Actually, regarding this, the first step is to write about the name of our file descriptor. Here our file descriptor name is fd.rname. And then we need to reference our list above. We need to reference the list above. We have our memory-file list. And then the next part is our output information. To be precise, what exactly should be written here in the output section? It includes the container ID from our share. Here, we are essentially extracting the variable for our container ID, and then through this, we output our final container ID. Ultimately, the content we are displaying here is just the final result we obtained, which is our container ID. Yes, our container ID. Under that container ID, we then write our specific content. Here, we are actually notifying notification information. The label is our file name. And here we finally put this, which is equivalent to the event level. Event level. Notification. Then for the label here, we write down the file name. All right, after writing this, we can directly go and check it. By using this detection file, we can then catch the container that is actually having the problem, and then through the container, we find the specific pod and then shut down the pod. This is the overall logic and process for this problem. Now let's take a look at the actual effect. And over here, first, let's save this file and then start executing. Start executing the specific detection process. The detection process. After we save it here, next we start executing our scan. Start executing the scan. And our file is the one we just wrote, the etc fa, and there's another file. And then what can you import the file into? You can import it into our log. You can import the file into the log. Here, our scan will take 30 seconds. Scan for 30 seconds. Let's take a moment to carefully examine the file we were just working with. I'm going to open it up now so we can see exactly what is going on under the hood. As I scroll through the contents, I am keeping a close eye out for anything that looks out of place. Wait, hold on a second. I think I see something right here. Yes, there it is, an error message buried inside the code. It is quite prominent once you know where to look. Let's break this down. If you look closely at the log entry, you will notice a specific name associated with the failure. It seems to be tied directly to the EV module, which is interesting. Furthermore, if you scan the memory allocation section just below that, you can see where the system hit a wall. This is a classic example of how these logs point us toward the root cause. It is a clear indicator of a memory conflict involving the EV component. By isolating these variables, the log, the name, the EV reference, and the memory usage, we can start to piece together a solution. We just had an error message here. Where is it? In the log here, right? There is an error warning in the log here. After we finish executing this, we interrupted it here. Let's cat the final log content we have here to see some specific information inside. The warning just now actually doesn't have much impact. And finally, let's look for whether there is any ID. Where is our ID located? We are looking for the container ID. Looking for the container ID. Container share container ID. It's here in this position, right? Here we have a container ID. Let's take down the container ID. We are going to use the standard Docker command to find out exactly what the container ID is for this specific instance. Regarding this, besides, of course, everyone should note here that for the exam, there are two viewing commands. One is docker ps, and the other is crictal plus ps, which are also two ways to view containers. For this, when the time comes, if one of them reports an error, just switch to the other command to check. Okay, we see one here, right? Found this ID. And here, within this ID, we can finally see something. There is, and information is right here. There is something called CPU-something something, right? Some content with CPU-something something. And here we use what? We use our kubectl command followed by get pods to take a look, right? There is indeed one called CPU here, right? There is one called CPU. So what have we actually found here? We found the problematic content. We found the problematic content, which is that for our deployment, it corresponds to this CPU one that we checked at the very beginning. Hey, there's a second one, right? So here, what can we do? We can just turn it off. Just turn it off. So how do we turn it off? Here we can actually just manually scale it down. By using a manual scaling method, we can just change its quantity to 0. Here we change it to 0. The name is CPU. Equals 0. All right, after changing it to 0, let's check the deployment information again. Here we can see 0 out of 0, right? For CPU, it's 0 out of 0, so that's no problem. So now we have successfully and normally shut down the problematic pod. And that is the solution to this problem. The only thing to note here is when we check the status of the containers, since there are mainly two types of containers, generally speaking, if the environment uses Docker, then use Docker PS to check. If the environment uses CRI, then just use the CRI control command to check the container information. And this is actually done through what? It's done by using the container ID we scanned to lock onto the pod information, then finding the deployment name inside the pod, and finally using our command to change the number of pods in that deployment to 0. That is the solution to this problem. Everyone, please note here that after solving this problem, you need to press exit twice to log out. The first exit takes you back to the regular user, and the second exit takes you back to the very beginning. Then you can proceed to the next question and start the next topic remotely. Alright, that covers the content of our fourth question. Okay, so that's it for this question today. If you have any questions or doubts, feel free to discuss them in the comments section below. If you need the complete question bank, you can also send me a direct message. Alright, that's all for today. Bye everyone.